Salam everybody. So today's lesson is about how can we solve some past paper questions about the organic chemistry. So let's start with 2016 May-June. 2016 May-June. Okay. Variant 1. Okay, so let's start with the first part. The question says, this equation is about molecules with molecular of C4H8. So once you look at a compound or a molecule with this formula, it indicates that you have to put in your mind, you could have alkene, okay, or you could have cycloalkane, okay. So these are have the same general formula. Okay, so let's start with the first part. Part A says, give the structures of the pair of positional isomers. It says that positional isomers, and once you are asked something about that, you're gonna change the position of the functional group or stuff like that. So if you're gonna deal with the cycloalkane, then it doesn't work for making a positional isomer because you have cycloalkane, like looks like square. So you can do something like positional in this case. So we can cancel the idea of cycloalkane. Then the probability of having alkene is the dominant. How can I draw the positional? You have 4 carbons, okay? And you can draw them like C, you can put the double bond in here, and you can put it in this case. All right, so you can have the double bond in the first carbon, or you can have the double bond in the second carbon. But put in your mind, the question needs the structures. We're gonna start with the structural formula. So you have to translate the word after writing that. Okay, you have to cancel that by the way, and just like try to rewrite it in terms of structural formula. So you have to write CH3, CH2, CH, double bond, CH2. So it works. Or if you don't like to show the double bond, it works by the way. You can write it like CH3, CH2, CH, CH2. So once the examiner see that there is no bond in here, but you notice that the carbon makes 4 bond, then we probably have a double bond in here. So you can write it either in this way or in this way. I prefer this one because it's clear. Okay. So this is the answer of your compound. And let's translate this to a structural. You have CH3, you have CH, CH, CH3. So this indicates that you have a double bond between the 2 CHs in this case, and this is positional. You're changing the position of the double bond. Here, the double bond is in the second carbon. Here, the double bond is in the first carbon, and that's why we can consider it as positional. Okay. Let's go to B. The B says, give the structures of pairs of a chain. When we say chain, it means that you're going to draw it in chain and branch formula. Okay, with formula of C4H8 and don't accept the stereoisomers. We don't care about the geometrical isomers like cis and trans in this case, or the chiral centers and optical isomers. So let's have a look. When we say chain, that you're gonna start dealing with alkene, you're still in alkene, but we have to make it one of these in a straight chain and one of these in a branch form. You can do it in structural form, and you can say like C, double bond, C, C. So this is a chain, okay? How can I draw it in a branch form? You can say you have a double bond, okay, C, double bond, C, and you have another C in here and another C in here. Okay, so we have to translate these to structural formulas. So we can say like this is CH2, double bond, CH, CH2, CH3. And here, if I want to draw it, you can draw it like CH2, C, and this is CH3 by the way, so you can like open a bracket and write CH3 by 2. So this is another structural formula in this case, and you can show me the double bond in here by the way. You can write it with a double bond or without double bond. Both are correct, but I still prefer to draw it in form of the double bond. So you can draw it like CH2, double bond, C, and this C is bonded to 2 methyl groups, and it looks like this. So this is the good answer for your compound. Okay, so this is a branch, and this is straight chain, and this is the ideal. So let's go to C. C says gives the structures and full names of the pairs of stereoisomers of C4H8. So we just remember something. This is a butene, and the butene in this case, you could draw it, and let's go back here. You can put the double bond in the second carbon or in the first carbon. But if you're dealing with stereoisomers, you have to take this form when the double bond is in the second carbon, not in the first carbon. Why? Because if you draw it in the first carbon like this, CH2, and you make C double bond, CH, CH2, CH3, you won't have a stereoisomerism if you have a carbon on the double bond that has two identically grouped in this case. So we don't have stereoisomers on this formula, let's say in this compound. So you should deal with the butene when the double bond is in the second carbon. So I'm going to show you this like C, double bond C, you have CH3, CH3, and here you have hydrogen, and you have hydrogen. You notice that the methyl groups are on the same level, and here hydrogens are on the same level. So this compound is called cis, okay? So this is cis, okay? And the longest chain that you have 1, 2, 3, 4, which means butene. You have to write but, and the double bond is in the second carbon. You had to make hyphen and 2 and then in. Okay, so this is your compound. Okay, you can draw that, or let's say describe the cis in terms of a symbol, which is Z. Okay, Z comes from a German word which is Zusammen, and it means together. So you can say Z, but if you just like to enhance your questions, it's up to you, but both are correct. And let's go to the trans. So you can draw the same formula, but the methyl groups are in the opposite directions, like CH3, and here you have hydrogen. You have the hydrogen and you have CH3. Okay, so how can I translate this to name? First, you have a trans. Okay, so this is a trans. I'm gonna use this is a trans, and you just make a hyphen. You have a butene, and the position is in the second carbon. You have to draw hyphen and then add in, or you can use the letter E. You can say E, but, to, in. So both are correct, and yeah, that's it. Let's go to the second one. It says that the structure of a molecule of a formula which is C4H8 is shown. It draw a functionally group isomer of molecule A in box B. Explain how molecule A and B could be distinguished by a chemical reaction. Okay, let's go to the beginning here. We told you that we could have cycloalkane or alkene. Okay, so if we have cycloalkane in here, then we have alkene in this case, right? We have alkene. So we have two probabilities. You can draw the all possible alkenes that we have. You could have the C, H2, double bond, CH, CH2, CH3. Okay, or you can change the double bond in the second carbon. The most important thing here, you have to draw alkene. Okay, so don't care about the position of the double bond in here. So you can draw it like this, or you can draw it like CH3, CH double bond, CH, CH2, okay? Or you can do it in a branch form, which is CH2 double bond, C, and you open bracket CH3 by 2. So all of these are correct because these are alkenes. Perfect. The question says, how can I distinguish compound A from B? The answer is we will add aqueous bromine. Okay, you have to add, or let's say Br aqueous, Br2 aqueous. Okay, so once you add Br2 aqueous, the observation for cycloalkane, it will be no change, but for the alkenes, you will have something called addition reaction. Okay, you will have addition reaction. Okay, addition reaction. And the compound that you will have in this case is dibromo. Okay, I mean the double bond will be broken and we will have two bromine atoms on both sides of the double bond. And the observation that you will have The orange, which is the bromine in water, the orange is discolorized, okay? So the compound here will change from orange to colorless, okay? From orange to colorless once you have alkane, and no change once you have cycloalkane. Okay, so let's complete a question 5. The question 5 says a reaction sequence is shown. Okay, show on the sheet. You have reaction. The starting material of this reaction is bromoethane, which is halogen alkane. We did several steps, as we can see. And let's start with the first question, which is A. A says complete the diagram to show the mechanism of reaction 1. Okay, we have reaction 1, as we can see. We want to draw the mechanism. Include all necessary charges. You have to put in your mind these things: necessary charges, okay, partial charges, lone pairs, and curly arrows. So how can I translate all of this stuff to get the 2 marks in here? Okay, you have to look at the halogen alkane. This is primary halogen alkane. And once you have a reaction of halogen alkane with a nucleophile, then it's SN2, okay? Which means that you won't have carbocation, no carbocation in this case. So this process will take place immediately and very fast and in one step. So look at this in here. We have bromine, which is partially negative since it's electronegative atom. As a result of that, the carbon that is attached with is partially positive. Okay, and you have, in this case, you show me the partial charges. And we have lone pairs. You have CN, and you have to put in your mind the lone pairs and the CN are on the carbon. So you have to show me the lone pairs on the CN, and we have to show you the curly arrows. So the curly arrows will attack the partially positive carbon, and put in your mind the head of the arrow is toward the carbon, and this reaction takes place only in one step. So this bond will be broken in here, as we can see, okay, and the electrons will go to bromine atom, and it will change to bromide. So in this case, this reaction takes place in only one step since you have primary halogen alkane. This is primary halogen alkane because it's bonded to only one methyl group, and that's why it will take place in SN2 mechanism. Okay, so you'll have this compound, and you notice that the bromine appears as Br negative, and here we have the charge of this compound. So in this case, if you draw all of these stuffs, you will have a full mark and you will take the 2 marks in here. Okay, let's go to the second one. It says that give the name of the type of reaction involved in reaction 3. So you have to go to reaction 3. As we can see here, we have reaction 3. You have carboxylic acid, and will change to W. And look at the agent here. You have lithium tetrahydroaluminate, which works as reducing agent. It will reduce the carboxylic acids to alcohols. Okay, all right. So what do we call this process? When the carboxylic acid is changed to alcohol, this process is called reduction. So this reaction is reduction reaction. Okay. Let's go to double I. The infrared spectrum of a propanoic acid produced by reaction is shown in 2. So this graph shows the propanoic acid. We just noticed that the IR diagram shows the functional group, and once we have a propanoic acid, it means that you have C double bond O, you have a band of C double bond O, and you have another band which is for OH. So we're supposed to have a strong peak at the area which is around 1,700 and a broad band which is around 3,200. So this is for propanoic acid. The question says, describe and explain the main difference. We need the main difference between infrared spectrum of W. So we can say that W here, we just saw it here, the W is alcohol, okay? Because you have carboxylic acid, the carboxylic acid is reduced by lithium tetrahydroaluminate and to W. So this is W, which is alcohol. So in this case, what do you think? When you change into alcohol, this strong peak will disappear, and the only peak that you will see is this broad band as a result of alcohol. So what you can say, or let's say, how can you describe these issues? Okay? You can say due to the loss of C double bond O, which has a mark, no peak or band will appear at 1680 to 170. So this range will be given to you in the data booklet, so you can take it. It's not for memorizing issues, so you have to put that in your mind. Okay. C, reaction 5 and 4 use the same reagent. Okay. Give the reagent and conditions needed for reaction 4. We have to go to reaction 4. Okay, where is reaction 4? As we can see, reaction 4 indicates that you have a Br that will change to OH. So this is a nucleophilic substitution reaction. And if you revise that, you have to put in your mind the reagents are sodium hydroxide, okay, or potassium hydroxide. And in this case, the conditions must be in aqueous form, okay? It must be in aqueous. It must be in aqueous. For reaction 5, give the condition needed for the reaction. As we can see, if you go for reaction 5, you have a halogen alkane and it turned to double bond. So this reaction is called elimination. And we have the same reagent, but the condition here is different. So the condition to make elimination a process is using ethanol as solvent. So this is ethanol, the conditions. Yes, the conditions are ethanol and heat. Okay, let's go to D. Under appropriate conditions, ethanol and propanoic acid undergo a condensation. So once you have ethanol, alcohol, and carboxylic acids condensation, this is the esterification process. State the conditions necessary for this reaction. Put in your mind, if you want to make a esterification process, you have to use concentrated acid. Okay, you can describe it in this form. And most likely the acid that is used is concentrated H2SO4, which is sulfuric acid. If you were asked about the role of sulfuric acid in this case, it works as a catalyst. Okay, it works as a catalyst. All right, so these are the conditions for making this compound. So it says that you have a propanoic acid and you have ethanol. Draw the skeletal formula of organic product of this reaction, which is ester. So we have to draw propanoic acid apart. Let's say you have 3 carbons, CH3, CH2, C double bond, OH. This is a propanoic acid. You have 3 carbons. You have the functional group of acids and the term of the molecule. You have ethanol, which means 2 carbons are bonded to OH. You have CH3, CH2, OH. So once you make this reaction, you have to take this part, okay, and then replace it by the hydrogen, okay? So the product in this case looks like CH3, CH2, C double bond, you have O, CH2, CH3. But put in your mind, once you draw that, you have to look again, you have to read that it needs a skeletal formula. You have a skeletal. So once you write this compound in here, like your pencil, whatsoever, you have to translate it to skeletal formula. Don't write this as answer. How can I draw that? First of all, you have one, okay, just one draw it. 1, 2, 3, okay. You can say 1, 2, 3, and here you have double bond, okay, and you have oxygen, and you have 1, 2, then it looks like 1, 2. This is the skeletal formula of the compound. You have 1, 2, which is ethyl, and you have 1, 2, 3, which is propanoate. If I ask you about what do we call this compound, and you name this compound, we start naming the esters from this part, which refers to alcohol, and then we can say this is ethyl, okay, and this part is called propanoate. So this compound is called ethyl propanoate. So this is the name of your compound. It says that V reacts with acidified manganate ions into different ways depending on the conditions. So once you notice that you have manganate, different conditions, you have to remember something when we have cold and dilute and hot concentrated. We are supposed to talk about alkenes. So here we have V. This V reacts in two different ways with cold dilute, acidified manganate, and here with hot concentrated. In addition to that, just let's say to make sure that you have alkene, it says that V decolorizes bromine water. So we're supposed to have alkene 100%. Okay. It says that when acidified manganate is hot and concentrated, propanoic acid only the organic product. When we say we have only one product, it means that you have symmetrical alkene. Okay, and it says that when acidified manganate is called dilute, the organic product T has two chiral centers. All right, give the structural formula of V and T. So let's start with V. It says that we have only one product, which is carboxylic acid. Okay, I just want to go down here and just draw some issues. You have only product, which is a propanoic acid. I want to draw it down there in here. CH3, CH2, C double bond, OH. I just want to revise something. When do we have carboxylic acid? When we have oxidation of alkene. It says that if you have C double bond C and it has hydrogen and it's bonded to other R groups, when we have oxidation with concentrated in hot acidified manganate, the H here will change to OH and the double bond will have O. So as we can see, we will have C, the H changed to OH, the R remains the same, the double bond have oxygen. Okay, so what to do in this case? You have to draw the two acids, okay, but let's say two molecules combine to each other again. What do we do in here? I will draw the double bond like C double bond O, and here we have OH, U, yeah, and we have CH2, CH3. And we have to draw the same carboxylic acid, which is C double bond O, and here we have OH, and here we have CH2, CH3. So we're supposed to have, we're gonna get rid of oxygens. So we can say that your compound or the alkene looks like C double bond C, which are in here, and we have H, and we draw the stuff in here, CH2, and we have CH2, CH3, CH3. So according to what we see, our compound is hexene. But where is the double bond? The double bond is in the third carbon. This is 1, 2, 3, 4, 5, 6. So this is hex 3-ene. So your compound is hex 3-ene. So the structural formula of the compound is CH3, CH2, CH, CH, CH2, CH3. Okay, and you indicate that CH is here, we have double bond in this area, or you can draw it in this case, like if you want to show the double bond, it's okay. CH2, CH, double bond, CH, CH2, CH3. So this is the answer in this case. All right, what about T? It says that T is a compound that is produced as a result of cold acidified. What do we have to conclude in here? Once you make a reaction by adding cold material, I just want to get rid of that in here, we don't need it. Okay, you have to put in your mind, if you make acidified in cold conditions, you will break the bond, the double bond in here, so we have to delete it. Okay, and we will have two OH groups on this case. We have OH in here. Okay, so this is the compound that you have. If I want to translate this to a structural formula, you will draw CH3, okay, CH2, CH, and you have to open a bracket and put the OH, and then you have CH, and we have another OH in this case, and CH2, CH3. So this is the structural formula of the compound. If you look at this carbon in here and in here, do we have chiral centers? If you look at this carbon, it's bonded to OH and CH2, CH3, and hydrogen, and we have another C that has OH, and yeah. So do we have 4 different groups? Yeah, we have this and this and this, and this is different. So we have 2 centers, or let's say 2 chiral centers in this case. So this formula will be drawn in here, okay? Identify the types of stereoisomers shown by V and T. We notice that V is alkene, and we can show the geometrical isomers. So you can say like geometrical isomers, or cis and trans. Yes, so it works. Yeah, I can write that. And for T, you notice that you have chiral centers, and these are called optical isomers. All right, so that's it. And yeah, good luck.